Right now, if you step outside in Saskatoon, the sky is just completely brown.
Yeah, this wild.
Literally, the wind is blowing over commercial transport trucks out there. The visibility is at zero, and it's not from a snow squall. It's from aerosolized topsoil.
Right, it looks like archival footage from the 1930s Dust Bowl.
Exactly. But it's not historical footage. It is May 13th, 2026. So for today's deep dive, we are looking at the invisible atmospheric mechanics that turn the seemingly flat, serene Canadian prairies into, well, one of the most violent weather engines on Earth.
Yeah, we're unpacking a really dense stack of meteorological data today, and it is focused entirely on extratropical cyclones. These are those massive mid-latitude, low-pressure systems that basically dominate the weather patterns across Alberta, Saskatchewan, and Manitoba.
I mean, they deliver almost all of the region's agricultural precipitation, right?
They do. But as the current crisis in Saskatoon is showing us right now, they are also the primary architects of these devastating sky-darkening dust storms, and on the flip side, those paralyzing winter blizzards.
Right. And to understand how these absolute monsters operate, we really have to trace them back to their birthplace. Because looking at the surface pressure maps in our sources, the genesis point for an overwhelming majority of these systems sits right on the eastern edge of the Rocky Mountains.
Yep, the topography of the continent itself is the catalyst.
So it's not just random airstreams colliding, the mountains are actually doing it.
Exactly. The meteorological term for this is lee cyclogenesis. So the leeward, or the downwind slopes of the Canadian Rockies and the foothills, they form this geographical transition zone, and it ranks among the highest frequency regions for cyclone generation anywhere in the northern hemisphere.
Wow. Anywhere in the atmosphere.
Yeah, it's incredibly active, and it's driven entirely by fluid dynamics.
Yeah.
Specifically, the conservation of potential vorticity.
Okay, here we go.
The fundamental equation governing this states that potential vorticity equals zeta plus f, all divided by delta z.
Okay, wait, let's unpack the physics of that equation for everyone listening, just so we can visualize this. So delta z, that represents the vertical thickness of a given column of air.
Right.
So imagine a piece of dough, or like an accordion. If a strong westerly wind forces a massive column of air up and over the Rocky Mountains, that column gets physically compressed.
It's squeezed between the rising terrain of the mountain slope and the highly stable upper layer of the troposphere.
Right, so the accordion gets squished, the vertical height built shrinks.
Exactly. And because the total potential vorticity has to remain conserved, it's a fixed value, the mathematical numerator in that equation, the zeta plus f part, has to decrease proportionally to match the squished bottom half.
Got it.
Now, the F is the Coriolis parameter. That just represents the rotational influence from the Earth's spin.
Which doesn't really change much, right?
No, at a fixed latitude, F remains relatively constant, so the variable that actually has to change is zeta.
And zeta is the relative vorticity, the air mass's own internal spin.
Precisely. So for the top half of the equation to drop as the air is compressed over the peak, zeta actually trends negative. The air mass acquires this slight clockwise anticyclonic spin, and it usually deflects slightly southward as it crosses the continental divide.
Okay, but the sources say the real violent action happens on the descent, right?
Oh, absolutely.
Because once that compressed accordion clears the mountain peaks and drops off the cliff into the Alberta plains, the physical constraint of the ground just vanishes.
Right, so the air column rapidly stretches out vertically.
Delta Z suddenly gets massive, which means the relative vorticity, the air's internal spin, has to spike dramatically just to maintain the mathematical balance of that equation.
Yeah, that dynamic is known as vortex tube stretching. The atmosphere is forced to compensate for that sudden, massive vertical expansion by generating intense counter-clockwise spin.
It's just wild to me that the mountains are basically imparting a mechanical twist to the wind.
They are. They force a localized surface, low-pressure system to organize right there on the plains.
But wait, the topography alone is just the spark, right?
Yeah.
Because the data indicates that roughly 25% of these newly born lows just kind of spin themselves out.
Yeah, a lot of them remain weak, localized disturbances, and eventually dissipate. They lack a secondary ignition source.
So what actually escalates them from a localized pressure drop into one of these massive extratropical cyclones?
They have to synchronize with an upper-level trough.
Like a disturbance in the jet stream.
Exactly. If the surface low created by the mountain is the fuel bed, the jet stream moving overhead acts like an industrial chimney. It creates this powerful updraft that accelerates the entire system.
Okay, so the jet stream is sucking the air upward.
Right. That upper-level divergence exhausts the air from the center of the storm much faster than the surface winds can rush in to replace it.
Which makes the surface pressure plummet.
Yes. And as the central pressure drops, the system intensifies its rotation. It starts reaching further and further out to pull in these starkly different air masses.
So it's drawing down dense, cold air from the Arctic.
And simultaneously pulling up warmer, more humid air from the south.
Right. And that severe temperature clash is the baroclinicity.
Exactly. That temperature gradient provides the relentless thermal energy required to sustain the cyclone and really expand its footprint.
So the mountains build the engine, but the specific latitude where this engine drops off the mountains fundamentally dictates the storm's character, doesn't it?
It absolutely does. It is a divergence and evolution based entirely on geography.
Right, because if the system forms up north in the Alberta Rockies, you get the Alberta Clipper. But if it forms further south, you get a Colorado low.
Yeah, the track defines the whole threat profile.
So let's talk about the Clipper first.
Well, the Alberta Clipper is locked into the northern branch of the polar jet stream, so it is defined by incredible forward velocity. We're talking about a storm tracking southeast across the prairies at speeds between 48 and 80 kilometers per hour.
That is moving fast.
Very fast. And because of that rapid transit and its high latitude origin, it spends very little time over open water or deep moisture sources.
Right, which makes sense when you look at the precipitation totals in the historical data. I mean, a Clipper might only put down like 8 to 15 centimeters of snow. And, you know, for a Canadian winter, 15 centimeters of dry powder is hardly a state of emergency.
No, not at all.
But then you see these localized nicknames recorded in the sources, the Saskatchewan Screamer or the Manitoba Mauler. That points to a completely different kind of hazard.
Yeah, the primary danger of a Clipper isn't the snow accumulation, it is the sheer thermal shock.
Right.
This fast-moving system is basically a high-speed delivery mechanism for pure Arctic air. Its cold front pulls down a massive lobe of polar air right behind it.
So you could step outside for a relatively mild morning.
And by the afternoon, as the front passes, the temperature profile collapses by 11 to 16 degrees Celsius. And that happens in a tight 4 to 8 hour window.
Wow. Just a sudden flash freeze.
And it's coupled with sustained wind speeds that easily exceed 72 kilometers per hour.
So the threat goes from just a little snow to extreme life-threatening wind chill. And I guess the violent mobilization of whatever loose snow is already sitting on the ground.
Exactly. It just blasts the existing snow around. Now, contrast that with the Colorado low.
Right, our second beast.
Yeah. It develops on the leeward slopes further south, typically over Colorado or the Central Plains, before it hooks northeast directly into the Canadian prairies.
And because it isn't caught in that same high-speed upper atmospheric flow, it lumbers. I mean, it moves at a fraction of the speed of a Clipper.
That slow forward progression is key. It gives the Colorado low the critical time it needs to drastically deepen its central pressure.
Like, how deep are we talking?
We frequently see these systems drop from a standard 990 hectopascals down to 977 hectopascals.
Wow.
Yeah, which generates ferocious winds. But more importantly, its southern position allows its counter-clockwise circulation to reach out and tap directly into the Gulf of Mexico.
So instead of a dry, fast freeze, the storm acts as an atmospheric river pump.
That's a great way to put it. It hauls immense volumes of warm, deep moisture, thousands of kilometers north.
And when that Gulf moisture finally collides with the sub-freezing air sitting over the prairies,
you get heavy, wet, concrete-like snow and devastating freezing rain events that just linger over the same region for days because the storm is moving so slowly.
which brings us directly to the blizzards, because I think people hear blizzard and they just think, oh, it's snowing really hard.
Right, the term is heavily diluted in public discourse.
So what is the actual meteorological criteria for a blizzard in our sources?
Scientifically, the definition revolves entirely around wind velocity and visual impairment. The actual precipitation rate doesn't technically matter.
Really, it's not about the snowfall rate.
Nope. To officially classify as a blizzard, a system must produce sustained winds over 40 kilometers per hour, coupled with blowing snow that reduces visibility to 400 meters or less.
Okay.
And this is the crucial part. Those conditions must persist unbroken for at least 3 to 4 consecutive hours.
Wow. And the sources point out the Red River Valley, which spans the Manitoba-North Dakota border, as being uniquely vulnerable to those specific parameters.
Yeah, because its topography is exceptionally flat. It creates this unbroken wind tunnel that just exacerbates the already tight pressure gradients of a severe Colorado low.
Which perfectly explains the March 1966 historical case study.
Yeah.
Because that event seems to illustrate this mechanism operating at its absolute peak.
Oh, the 1966 event is legendary. It featured a pressure gradient so compact and intense that it drove hurricane-force winds straight across the plains.
Winnipeg recorded sustained gusts of 113 kilometers per hour.
Yeah, and the sheer mechanical force of the wind at those speeds actually polarizes the snowflakes in the air and turns them into this microscopic abrasive powder that just completely blinds the entire region.
The sources noted that the city endured 14 straight hours of absolute zero visibility. 14 hours.
It's terrifying.
And the wind didn't just blow snow around. It constructed these structural, 3-meter-high drifts that entombed entire residential blocks. People in downtown Winnipeg were relying on snowmobiles for emergency transport because the roads basically ceased to exist.
It is a staggering display of atmospheric power.
But it gets worse, right? Because the data shows these cyclones don't just act in isolation.
Right.
Look at the April 1997 storm, the one they call Hannah. That perfectly demonstrates how a Colorado low can trigger massive compound disasters based entirely on the pre-existing conditions of the ground it travels over.
The ground conditions are everything. So the 1996 to 1997 winter season had already deposited a record-breaking snowpack across the entire Red River Valley basin.
Right, so the soil was totally saturated and the surface was locked under millions of tons of frozen water.
Yes. And then the Hannah storm arrived in early April. Now, this is a time when the region is typically looking for a gentle spring thaw, but instead, the storm imported massive quantities of warm Gulf moisture directly into this deeply frozen environment.
And it started as freezing rain, didn't it?
It did. A paralyzing freezing rain event. It coated infrastructure in heavy ice and just shattered local power grids.
And then the thermal profile of the storm shifted.
Exactly. The temperature dropped just enough that it dumped an enormous load of heavy, wet snow directly on top of the existing record-deep snowpack.
Which sounds bad, but the thermodynamics of rain-on-snow events are what actually make it a nightmare.
Yes, it's highly destructive. The latent heat that gets released as the incoming rain freezes actually accelerates the melting process of the underlying snowpack.
So it's melting from the inside out.
Exactly. The hydrological overload was absolute. When the system finally cleared and ambient temperatures rose, the sheer volume of water entering the completely flat, northward-flowing Red River simply had nowhere to drain.
Right. The river just expanded beyond its banks into this massive, slow-moving lake.
It triggered a catastrophic 500-year flood event.
A 500-year flood. And the sources show the city of Grand Forks was completely inundated. They had to execute an emergency evacuation of 52,000 residents.
And it inflicted over $4 billion in structural and agricultural damage. The cyclone itself had passed, but the disaster it triggered was literally just beginning.
And that compound effect, the way the ground's condition amplifies the storm's impact, that brings us right back to the May 2026 crisis happening right now in Saskatoon.
It really does.
Because if you take that exact same extratropical cyclone engine, but you switch the antecedent condition from a frozen flooded basin to a severe prolonged drought,
The threat transforms entirely.
the hydrological overload becomes an atmospheric blackout.
Yeah, the mechanics of the cyclone's cold front are mathematically identical. The advancing cold air mass is incredibly dense, so as it moves across the plains, it acts like a physical wedge.
Just aggressively undercutting the warmer, lighter air ahead of it.
Right. It forces explosive vertical lift. And if the region is gripped by drought, the topsoil is totally desiccated. It's devoid of the root structures and the moisture that normally anchor it to the earth.
So the storm's updraft just vacuums the landscape.
Exactly.
But these extreme dry spells don't just happen by accident. The sources make it clear that the preconditioning required for these massive dust storms is typically driven by macroclimate patterns.
Yes, specifically the El Niño Southern Oscillation, and more particularly La Niña.
Right, La Niña.
Because La Niña conditions frequently induce these massive stationary high-pressure anomalies known as blocking ridges over western North America.
Okay, so visualize a blocking ridge as like an atmospheric boulder sitting right in the stream of the upper level flow.
That's a perfect analogy. And they force the moisture-bearing Pacific storms to divert. They either go far to the north into the territories or far to the south into the United States.
Effectively starving the Canadian prairies of precipitation for extended periods.
Yes, the soil moisture deficit just compounds month over month.
Which is exactly what we saw the ultimate culmination of during the 1930s. You had decades of blocking ridges, combined with those deep plowing agricultural practices that basically pulverized the soil structure. The entire region was primed.
And when the spring extratropical cyclones swept through, they leveraged those 128-kilometer-per-hour winds to loft fine particulates 20,000 feet into the troposphere.
Creating towering walls of dirt that literally blotted out the sun.
Right. And a very similar convergence of meteorological factors occurred in 1988, too.
Oh, the 1988 drought.
Yeah, a persistent winter blocking high prevented any meaningful snowpack accumulation. So without that slow, steady spring meltwater to recharge the shallow groundwater aquifers, the soil profile completely degraded by May.
So when the dry spring cyclones arrived, bringing intense pressure gradients but no actual precipitation, the vertical lift just stripped the agricultural topsoil with terrifying efficiency. And that is the exact synoptic setup we are watching unfold today, May 13th, 2026.
Sadly, yes.
A highly dynamic low-pressure system has just stalled over central Saskatchewan. It is grinding against a high-pressure zone to its south, which is compressing the isobars and generating 110-kilometer-per-hour westerly gusts across the province.
And because the preceding spring delivered virtually zero meaningful precipitation, the topsoil is completely loose.
And now these sustained winds have triggered highly unusual red dust storm warnings from national meteorological agencies.
The physical density of the airborne dirt right now is overwhelming infrastructure.
Yeah.
It's shorting out power substations, clogging mechanical intakes, and paralyzing transportation corridors.
The cyclone is simply exploiting the severe vulnerability engineered by the prolonged dry spell.
Exactly.
And watching this compound disaster unfold in real time really forces a hard look at the long-term climate projections outlined in our sources. And I have to say, the data presents a highly complex paradox here.
It does.
Because as global atmospheric temperatures rise, the climate models indicate that the overall frequency of these extratropical cyclones forming across the prairies is actually projected to decrease.
Right, which seems highly counterintuitive.
Yeah, wait, less frequent means we're safer, right?
Well, you have to examine the mechanism of Arctic amplification. The Arctic region is warming at a significantly accelerated rate compared to the mid-latitudes and the equator. Now remember that the fundamental fuel for an extratropical cyclone is baroclinicity, that stark temperature gradient between the freezing northern air and the warm southern air.
Oh, so a rapidly warming Arctic effectively reduces the available thermal energy.
Exactly. The temperature contrast isn't as sharp, meaning fewer storms possess the energy required to successfully spin up in the first place.
Okay, but fewer storms do not translate to a lower threat level, do they?
No, not at all, because the reduction in the north-south temperature gradient also dramatically alters the behavior of the jet stream.
And the jet stream is the very thing steering these storms.
Right. The speed and intensity of the jet stream are directly driven by that temperature clash. So as Arctic amplification reduces the gradient, the vertical wind shear weakens.
The upper-level steering currents become sluggish.
Very sluggish. They become prone to these massive meandering loops. Consequently, the extratropical cyclones that do form move much slower. They lose their forward momentum.
Oh, wow. So instead of a fast-moving system passing over Winnipeg or Regina in, say, 12 hours, it stalls.
It stalls out entirely. It lingers over a single watershed or agricultural zone for days, continually amplifying whatever atmospheric payload it is carrying.
And because of the Clausius-Clapeyron equation, that payload is significantly heavier than it was in the past.
Yes.
For those who might not know, the Clausius-Clapeyron relation dictates that for every 1 degree Celsius of warming, the atmosphere's physical capacity to hold water vapor increases by roughly 7%, right?
That's right. It's a foundational principle of atmospheric thermodynamics. So a slower-moving Colorado low, tapping into the Gulf of Mexico, is now hauling a massive surplus of latent moisture.
And when that system parks itself over a region because of those weak steering currents, the precipitation totals just become astronomical.
Which leads to unprecedented winter blizzard accumulations and catastrophic spring flooding events. But the inverse of that equation is just as destructive, because higher baseline temperatures dramatically increase the evapotranspiration rate.
Yeah, it aggressively sucks moisture out of the soil and vegetation during those dry spells.
And this dynamic produces what the sources identify as the compound hazard risk.
Right. The baseline climate shifts toward prolonged, intense flash droughts, which are then abruptly shattered by these sluggish, supercharged cyclones.
It's a violent pendulum swing.
Extremely violent. A deep drought desiccates the soil, and then a slow-moving front arrives, unleashing highly destructive wind shear and dust storms.
And that is followed immediately by torrential, lingering rainfall that the baked, hardened earth cannot even absorb,
resulting in devastating flash floods that wash away whatever topsoil remains.
It's a relentless one-two punch. The sources highlight that in 2024 alone, Canada experienced $7.7 billion in insured damages, heavily driven by these compounding, overlapping extreme events.
It is a structural stress test on an unprecedented scale,
impacting everything from global food security to local grid resilience. Yeah, the mechanics of the atmosphere are endlessly complex, but the data clearly illustrates how rapidly the baseline behavior of these systems is shifting.
The raw kinetic energy remains, but the delivery systems are fundamentally evolving.
Exactly.
Well, we have traced a massive atmospheric arc today. We broke down the fluid dynamics of vortex tubes stretching over the Rockies and how that mechanical spin draws in polar jet streams to forge these massive, low-pressure engines. We examined the freezing, high-velocity thermal shock of the Alberta Clipper and the slow, moisture-laden devastation of the Colorado Low. And we've seen how these storms interact with the ground itself, triggering 500-year hydrological collapses in wet years and churning up the apocalyptic dust storms currently darkening the skies over Saskatchewan.
Which really leaves us with a critical pivot point to consider regarding our relationship with the environment.
How so?
Well, we currently engineer our cities, our agricultural supply chains, and our emergency management protocols around this core assumption that a storm is a transient interruption.
Right, we view it as an anomaly.
Yeah.
Something we simply have to weather before returning to a stable, predictable normal.
But if the climate models are correct, if slower, ultra-charged extratropical cyclones driving brutal pendulum swings between deep drought and catastrophic flood are the new permanent reality, how does that change our presence on the Great Plains?
Wow.
We may no longer be waiting out the weather. We may have to fundamentally redesign our civilization, our architecture, and our agriculture to exist continuously inside an atmospheric engine that never fully turns off.
That is a staggering thought. If the storms aren't just passing through anymore, we have to learn to live inside the engine. Thank you for joining us on this deep dive into the invisible forces shaping our skies. Stay curious, stay informed, and we'll catch you on the next one.